Ladies and gentlemen, first of all, I'd like to thank my dear colleague, Professor Uya, for giving me a cordial invitation and in particular the warm welcome. It's a very nice dinner every night. I'm here and I enjoy it. It was really, really great. Thanks a lot again. Now to chemistry, to flame retardancy. I'd like to talk today about efficient synthesis strategies and flame retardancies. I thought it will be interesting to discuss about these things because a lot of you guys are doing with synthetic chemistry and often you want to do for which aim is it good or what shall I do to create a very efficient flame retardant. So I hope it works. Okay, and so I'd like to talk today about, after a short introduction, about this flame retardant efficiency versus synthesis, about novel flame retardants, mode of action and functionalities, new synthetic strategies and starting materials, flame retardants and additional effects, some synergy discussions, radical generators as a new flame retardant on the market, and last but not least, some conclusions. Okay. First of all, as I said, it is really important to discuss what we are doing. What is the aim? What is the goal of our work? Should we do? No. We will do it so. This is better. Okay. Should we do research, fundamental research, to collect information, do some publication, because this is most important or very important for you, because most important is to finish your PhD or master, of course. This is, of course, we have to take care for safety, for eco-friendly, for life cycle impacts. This is basic or fundamental research. On the other hand, we should look for economy, for convenience, for costs. This is going in direction of the industries, looking for production. Is this the same? Your research work, your synthesis, your measurements compared to that, what the companies are doing. They have to look for green and sustainable synthesis and manufacturing. What this is, we will see in the next slides. And of course, for application. Okay, if I want to develop a new flame retardant, very important is, of course, first of all, flame retardant efficiency. That what is really important. You want to create a new flame retardant for a new polymer, and then the efficiency is really important. On the other hand, the compatibility with the polymer, material properties and other additives, and as well the processing of that polymer is important. Then viscosity, composites, abrasion, we have to look after. We have to look after this properties in our polymer. And then we should take care on the synthesis. Because if we have a very complicated synthesis, this is good. For the lab, it's okay. You get your substances in your hand. You can do something with that can incorporate in the polymer, can do measurements, and so on and so on. But for other application, often it is not enough. We will see later on. And then on the last part is environmental and health profile. In Europe, there is an organization so-called REACH. This REACH means restriction, evaluation and authorization of chemicals. That means if a new chemical will come on the market, we need this. Unfortunately, it's not expensive. It is very expensive. Sometimes. Depends on the amount you will bring to the market. Okay. This is the so-called green chemistry, which is really, really important if you will go for production. If you will bring your synthesis in an upscale. You see here, there are 12 principles developed 25 years ago and going more and more important. Here are the regulations, as I mentioned, the process, the procedure you will create for the chemistry and, of course, business needs. And that means, in other words, for your synthesis, it's not only important the yield, that is always important, or the selectivity. It's also important this so-called atom economy or atom efficiency. That means, in other words, we'll see it later on, we should take care not only to how many product I will get, you should also take care which side products and what is the amount of the side products are important, because these side products are often also very important for the final price. Okay, now a little bit more deeper in chemistry. You see here a simple overview of industrial phosphorus chemistry. And you see a little bit the amounts here. Phosphate rock, so-called apatite. It's we have every year 140 million tons to dig it from the earth. But most of that, of course, is going to fertilizers in agriculture and not in flame retardants, of course. You see here the following processes. You can do a dry process for fertilizing, and you can do a wet process to isolate phosphoric acid. That are only 30 million tons. Or you can do a reduction to white phosphorus done by carbon in an electric furnace. It's about 1 million tons per year. And then, of course, it is the whole way of phosphorus chemistry starts, of a little bit sophisticated phosphorus chemistry starts with white phosphorus. The easiest way is the green one, because you can do a disproportionation, and the one product is pH3. You are pretty familiar with that. And another product of that reaction is hypophosphorus acid, or the compared salts. It's about 50,000 tons per year. On the other hand, a very important process is the chlorination of white phosphorus. Final products are then PCl3, PCl5, and so on and so on. That is a little bit more expensive, because you start here a cascade of new reactions. Here you are immediately reached to products which can handle very easily. That's why this way is cheaper. Okay, and immediately we will see there is a final product on flame retardants made from that sodium hypophosphite or from the free acid, the so-called DEPAL shown over here, is a classical flame retardant produced since 20, 30 years ago, and you see it's only an addition of ethylene to that molecule to reach the sodium salt of this phosphonic acid, and incorporation of aluminium salts, you get the aluminium phosphonate over here. This is known as DEPAL. The producer is Clariant in Germany and Switzerland, and it's a very good flame retardant for engineering plastics, especially polyamides, polyester. And this is a simple radical addition. That means very, very atom efficient synthesis of that one starting from here. And another very important flame retardant is aluminium hypophosphite. It's only a salt formation of that molecule. And nowadays here aluminium phosphide by a simple oxidation or disproportionation again from here as a flame retardant developed by Clariant in the last couple of years, and this is a typical replacement for melamine polyphosphate in polyamide. That means with such simple reactions we have a very nice couple of flame retardants, that one, and that one, which are useful for some engineering plastics, for example. Not only useful, but also commercially available. But now we look a little bit deeper. We were here, and now we go to PCl3. We can synthesize these phosphites or phosphonates. We can synthesize POCl3 from here, or PCl5 and go to phosphocene from PCl3 to Topo, for example, as mentioned, and so on. That means, but if we look on that one, we should realize the more synthetic steps means more expensive flame retardants or more expensive substances. On the other hand, if it is fact, then we should realize these flame retardants should more efficient. You need less amount, then of course it can be more expensive. Okay. Now here some couple of reactions starting from phosphonates, for example, from that molecule. A lot of them are already known, but I like to show you what is going on if you think, if you want to synthesize such a compound, for example, an amide. You know this reaction very well. This is the so-called Edderton-Todd reaction. Here shown for benzylamine plus this phosphonate or phosphide gives by that under typical Edderton-Todd reaction this phosphoamide. The oxidizing agent is tetrachlorocarbon, and it's very wonderful for the lab. It works well. The yield is okay, but forget it for industrial application. The problem is this one. Strange and expensive ingredients for the reaction and a lot of side products here. Because in industries you are responsible for recycling or wasting. And that's why it is really important that this should very, very easy. And of course, there is a more simple solution. Look here, the same EDAC, the same starting materials. Over here the amine and here's a phosphide. And you see now we do it with copper iodide as a catalyst, and the oxidizing agent is now oxygen from air. This is really cheap compared to that one. And you get a reaction, the yield is okay, and the only side product is water. That is okay. And you see, this is 9 years old. 9 years ago, they described that. And not only for that reaction, they described 16 examples. This is good for fundamental research in the lab to synthesize one product first time and to check their properties or their properties regarding the incorporation in a polymer. This is more applied research if you want to go for upscaling or a production. But you see the differences. Okay, but back to that compound. This hypophosphorus acid or the hypophosphite salt you can do a simple esterification developed by Jean-Luc Moncham 20 years ago, and you get this ester done by a silicon. This ester is very nice, but not so much synthesis was made based on that material. There are a small review, again done by Professor Moncham. You see there are some reaction possible starting from here. And this is a really simple starting material, as I show you for the synthesis of dipal, for example. You can do a lot of things starting from here. And of course, another publication, a couple of years older, described that reaction. And the question is, perhaps we can use that one for a polyphosphamidal addition with diacrylates or diacrylamide. Or we can formulate it in an epoxy resin. An addition reaction in an epoxy resin is so-called preformulation. In the next slides, suggestions are all in orange. Okay. A group around Sergei Levchik from ICL-CP, Israeli company, he's working close to New York City, synthesized this ditopo and did some investigations only in epoxy resins. It is a little bit not so easy, that synthesis, because this is a classical organic synthesis. But it is possible, and you can see this molecule is pretty nice because you can do a lot of synthesis with them regarding of polymerization. It is interesting. You can do a polyphosphamidal addition with diacrylates and diacrylamides. Okay, next reaction. You see, Michael additions, I'm pretty familiar with this one. We have had, we will see a lot of more, and here we have a so-called oxa Michael addition. That means we have here a triol and a diacrylate, all commercially available, pretty interesting. And in one reaction, we can synthesize this hyperbranched polymer. This is very interesting nowadays because based on old synthesis we developed 20 years ago, these hyperbranched polymers have a very nice effect. For example, in epoxy resins or other thermosets, they are stabilize the class transition temperature or even improve these. And of course, you can synthesize this again and then do some phosphorylation, again with a phosphor-Michael reaction, on that acrylates, and then you have a very nice hyperbranched phosphorus compound for applications, for example, in epoxy psoriasis. Next problem. Often we have a really strange problem, and this problem is shown over here on the right-hand side. In Europe, we have a list, and this list is called SVHC, substances of very high concern. If a chemical is listed over there, then it will be banned if alternatives are possible or shown. That means these substances are very, very deeply investigated regarding to their toxicity or environmental benign activities. And if it is really strong, then they are not only a candidate, they are a fixed member of that list, and then this compound will be banned. And one of these compounds are fluorinated oligomers and polymers. And PTFE is Teflon, well known. Polytetrafluoroethylene means PTFE, is in a lot of industrial flame retardant polymers incorporated in a very less amount, about 0.5%. For example, or in particular in engineering plastics like polyamides, polyesters, ABS, and so on, polycarbonates. And this substance is responsible for anti-tripping. This has a strong anti-tripping effect. But if this materials will be banned, we have to look for alternatives. And one of that alternatives are described in the last years. Firstly, 2 years ago, this was described, the synthesis of this substance. Very easily, you form the shift base and then add this topo and get this molecule. That was only tested in epoxy resins, and surprisingly, the topo derivative, of course it's not surprisingly, acts in the gas phase very well, but there was observed a comparable huge amount of SHA, that means a condensed phase activity, and the authors said that is coming from that CN groups. And only 1 year later, another Chinese group published this, means last year, recently, and they used that one, again formed by the shift base addition of topo, the so-called Budovnik reaction, and you have the cyanate group over here, and they tested this flame retardant behavior in polyamide 6, and they found anti-tripping properties. And the reason for that, they postulated that reaction. That means cyanates can trimerize to form these very stable aromatic rings. And this is the reason for a higher char and the reason for this anti-tripping effect, they postulated. So, but the question is now, can we do this with other cyanates? As I said, one of my loved reaction is the so-called Meigel addition reaction, shown over here. We have a simple acrylate and a phosphor derivative with a pH bond, and we have in the synthesis way the simple addition to form that final product without any side product. And again, or much better, is the back reaction. this one is an elimination. That means this reaction is going back. We get an acrylate again, and it's an active phosphorus unit, which then does the flame retardant effect. Okay, of course we can not do this not only with DOBO. Here we have a DOBO OCP, here diphenylphosphine oxide, CC, and here phosphide OO. And of course these represents different effects. Here much more in the gas phase, here more in the condensed phase. And the thermal stability is growing up in that line. Okay. Then, of course, I checked the literature, because I must not check the literature, I know this. Of course, there is an odd reaction. We learned it in the third semester, that means in the second year of our studies in chemistry, the so-called Knoevenagel reaction. Odd reactions mostly known from German guys. It's difficult to talk, but anyway, he did the following. He used malodinitrile or malloester, or anyway, and did a reaction with aldehydes and form this one. Yeah, coming from here, going to here, get a wonderful CC double bond from a CO double bond. It's not so easy, but here works it well. But you have here strong electron withdrawing groups. And this molecule is of course able to add again with phosphides to form this one. Now we have a phosphorus unit over here and two cyanate groups. Pretty easy way, and there are a lot of work done. Here are some examples. Here this started from Z phosphorus unit, C from Z, same reaction, and you see very nice products, works always very well. And you see here really a lot of groups worked in that way. They did it in a simple 2+2 reaction, or in a one-pot reaction, in a two-member reaction, or here in a three-member reaction in a so-called one-pot reaction. Everybody can look for the best way in the lab to synthesize this stuff, but it is I think it is worthwhile to check it. You can incorporate phosphorus for flame retardancy and incorporate very easily these cyanates and look a little bit deeper about the anti-tripping or char-forming effect by cyanates. Here are a couple of more examples. As a catalyst, it's now a 1, 2, 3 component reaction in a one-pot scenario with iodine as a catalyst, and another one here in water with microwave application, and the last one again here with in a one-pot scenario, and synthesize this one very easily. Okay, next question. Very important is more and more changing to flame retardants coming from a molecular compound going to a polymer. The reason for that is as well this reach. Polymers are easier to get reach certification. That means you can just produce, or you can just upscale much easier than compared molecular compound. That's why we take a look for the cyanate phosphorus compounds as polymers, and it was described, and look here, first time this year, pretty new. Simple reaction, again we have a phosphorus containing diacrylate, and now this is malodinitrile and you get a polymerization reaction. And again, this is a poly-Michael addition. Very nice. And I can only recommend to do something here because it is easy to synthesize, and perhaps we can here change the groups, or here you can do this also with ester groups in that way, or a couple of cyanate and ester. There are a couple of possibilities are creatable. These guys unfortunately did it in PLA and looked not for tripping effects. This is only a review to see what is possible to create and phosphorus and different phosphorus acrylates. You have here a lot of possibilities. You can do this or not. Here are very interesting things. Of course, you can get acrylates from nature. If you burn meat on or heat it up in a pan, it will smell aggressive. It burns in the nose. This stuff is acrolein. And acrolein can you oxidize, and you will get acrylic acid. Very easy. And here are some synthetic and synthesis and polymerization of bio-based acrylates in a review. I recommend to use that compound or that one to add dopo or other phosphorus compounds and use it for polyurethane foams. We did it for this simple acrylate ester. We add dopo, and in case of isopropyl or propyl over here, we get liquids, which were very, very effective in polyurethane foams. And here you have lactants or that special compound where the addition of this dopo or other compounds is possible, and I think, to my opinion, also worthwhile. And you have direct bio-based source for this one. Okay, another thing, this is not it's not a new stuff. This is very old and commercially very well done. They use the simple epoxy resin and acrylic and do an addition of acrylic acid. Then you get typically set reaction here. You get this diacrylate adduct. It's called as vinyl ester in technical application. Sounds strange because it's acrylate and called vinyl, but anyway. And we thought perhaps there is some chemistry possible. You have here free OH groups, you can do phosphorylation. You have free acrylate groups, you can do phosphorylation. And you can do this only on that side, and so on and so on. But much more interesting, there is another stuff commercially available. This is triglycerol diacrylate. That means this here coming from glycerine or glycerol, triglycerol, and acrylate as well from nature. This is pure nature. And very interesting because you have free OH groups and you have acrylates. And you can see here you can do a phosphor-Michael addition. Then you have a phosphorylated triol. You can do Erdott reactions. Then you have a triphosphorylated diacrylate. You can directly use it for coating. And you can do, of course, a radical polymerization starting after the Erdott reaction. You can start a polyaddition. Here you will get a thermoset, here a thermoplastic material, and so on and so on. This is very, very versatile, to my opinion. And cheap, bio-based, and commercially available. Surprisingly, nobody did some chemistry with that until now. But it's not so bad. Okay, now back to itaconic acid, as well bio-based. I know this very well because the company I'm working for is doing some business with itaconic acid. And not only my company did it, also here in China, in the group of Professor Xu, he did a lot of chemistry with itaconic acid. Interestingly, is formed that dry epoxy resin here, which have nearly the same properties compared to GmbH, the basic resin. On the other hand, we can form this topo, or he forms this topo derivative as epoxy resin, or here do this interesting incorporation of forms that epoxy resin directly from the itaconic acid. The question is now epoxy resins. If you look a little bit deeper, you will figure out in the last 20 years there are about 1 or 2 new epoxy resins came to the market, not more. And the question is, of course, why? And the answer is they synthesized a lot of interesting stuff. For example, here this flame retardant, simple molecules, this tetrabrominated diphenol GmbH, or topo, or here some mono acid and D-phosphenic acid, or the topo adduct to quinone. And the question is, if you want to bring this in an epoxy resin, the simplest way is glycidylation. That means you do a reaction with epichlorohydrin. Epichlorohydrin, oh, thank you, very kind. But this stuff is really toxic, and the companies are working with epoxy resins don't like this. And the answer is, okay, before the answer will come, another slide. New developments are polymers, polymeric flame retardants shown over here, but all with functional groups, OH groups, for example, here and here and here and here. And as I said, the answer is why we can incorporate small molecules, small functional molecules in epoxy resins, and we can incorporate also their properties. The way is very simple. It's a so-called fusion process or reactive preformulation. Here, topo with a Novolac resin forms that one. Or this adduct of topo with the Novolac resin forms that one. You have here the original resin and here the bridge, or here the adduct. And now you can use it without any using of epichlorohydrin, and you have not only the molecule incorporated, but also the flame retardant property. Okay, see here some for the application. This is a cured epoxy resin. Important is the flame retardant is nearly the same here in that region. But important is that the glass transition temperature is compared to the neat resin only a little bit reduced, in particular for this polymer and the dimer over here. Okay, next thing. Now a German group developed these polymerics, polyester. Here malonic acid and here itaconic acid. And interestingly, they find two things. This is selective for UV-initiated cross-linking. That means if you irradiate this with UV, you only activate this group, and this not. But this, on the other hand, is selective for aza-Michael cross-linking. And this not. And this is very interesting because this is a very nice selectivity. And of course, I would think if we used instead of itaconic acid the dopo-adductive itaconic acid, which you can sometimes buy, instead of this poor neat itaconic acid, then you have now here a dopo derivative, but you have this again here active and can do SR-Michael cross-linking. Or on the other hand, we can do a Michael adduct of maleinic acid over here and have then an intact itaconic group for an UV-initiated cross-linking. And you have incorporated phosphorus. And can do, in both cases, flame retardant investigations. Itaconic acid, again, is very important for a couple of investigations. Here is in a hyperbranch polymer toughened epoxy resin with rapid stress relaxation, superb solvents resistance, and closed loop recyclability. Last year published again from this Chinese group. Okay, now back to small molecules with nice functionalities. If you want to go for polymers, as I said, it is really important sometimes. It's not only the registration in Europe, it's also a lot of other advantages which polymers have. For example, a better compatibility with the polymer. If you will incorporate one polymer with another, then it is a blending. And the blending is much easier to handle than to bring 20% of a flame retardant in your polymer. You will mostly is a blending for an improving of material's property responsible and additive mostly not. So the EDUCts or the starting materials for these polymers, of course, have difunctionality. Here's the dichloride, dichloride, dichloride. Or on the other hand, you have amines, for example. This one, piperazine, or this one, DDM, or this one, benzoguanamine. And interestingly, perhaps these molecules should be possible to synthesize. Then you have phosphorus incorporated. Should be possible if you use these dichlorides with the excess of piperazine. Okay, piperazine itself is used in a lot of publications. Here is one by a so-called substitution reaction. That means you use a chloride and an amine as a piperazine, 2 + 3 functional groups, and you get a thermoset or a cross-linked material now between phosphorus as a phosphorus amide. Okay, and you can do it, of course, as a chain molecule, as a in a polymeric chain shown over here. You can synthesize cis dichloride and do with piperazine a polymeric substitution to form this thermoplastic material. Okay, and a newer one published this year. Again, they use this benzoguanamine, which is going more and more popular, forms this chain again, and they used some, and they did some investigation here in the case of flame retardancy for PA6. It's interesting for PA6, but we will see later on more. Or this one, again, dichloride, and now we synthesize this diacrylate, and now we switch over from a substitution process to a polyaddition. Substitution, as you know, we have always a side material because we have to catch the HCl by a base and create some salt in the substitution process. Over here we have an addition process, a polyaddition process, and this is our starting material, and of course we can, with piperazine, form this polymeric stuff, for example. And then we have immediately a coating material, a resin, which can be used for different application. In that case, so it is UV active. Okay, another publication came from Sapir Khan from Switzerland. He synthesized a very, in a very difficult manner, this divinyl derivative, and do a polyaddition with piperazine to form this one, especially in a reactive extrusion, very, very special. But anyway, the reaction, of course, works well. Okay, radical generators, pretty new field. What I mentioned about the epoxy resins, which epoxy resins came out to the market in the last years, it's the same as in flame retardants. There are only a couple of flame retardants which came out pretty new on the market in the last 2 decades. It's really not much. It's no 10 new compounds were gone for upscaling or for production. And here we see a very interesting order information. This one, a simple phosphorus compound, and this one, it's a so-called NOR-Hals. Hals means hindered amino derivative, shown over here. And NOR means this group. This is not a flame retardant originally. This is a UV stabilizer. UV stabilizers are able to form radicals in a pretty easy way. And these radicals can catch other radicals. These are responsible for destroying our polymer and activated by UV. And a group, this is an English company, Thor, figured out that this material produced by BASF and this one produced by themselves can form synergistic formulations, especially in thin application. For example, polypropylene film or foils. Okay, sure, this is very important, of course, for thin application, more than for bulk application, especially by foils. And this together can work very well as flame retardant formulation, for example, in polypropylene. We will see later more. Here is shown what is going on. This molecule, as I said, can form radicals. We see here that was too fast. Okay. We can form this one. We can form some radicals over here pretty easily. And these radicals are pretty active to catch, as I said, reactive radicals like H or OH radicals coming from UV. But it's not only in UV irradiation important, it's also in the flame retardancy very important, because these H and OH radicals are catalysts in our fire circle or combustion circle, and catching them or scavenging them will extinguish our fire. This is a typical flame retardant acting in the gas phase. And these radicals coming from here, this flame step NOR 116, this is the structure, can form these radicals, and these are able to catch these. Here are the radicals formed, but of course simple molecules are relatively less stable. That's why we have to stabilize this. And we have 2 possibilities. One is a so-called steric stabilization. You see it over here. And another one is an electronic stabilization. by electro-withdrawing groups over here. If you do this or this, you will be able to stabilize that molecule for bringing in your polymer and guarantee durability and reliability. But on the other hand, if fire came out, these radicals will be these radicals will be formed and can catch our OH and H radicals. The same was done not with oxygen group here, but with sulfur groups by Kalle from Finland. Again, he did a steric stabilization of that group as well as an electronic stabilization. Same principle. And the same reaction, now forming N radicals and RS radicals. And these are very efficient. And he did not only a lot of investigations, shown over here, what is the real mechanism behind this action, forming that one and that one, and what is the action in the polymer. As I said, it is primary, it is only a gas phase active flame retardant, but a Korean company, Songwon, is buying the patents and do some production. And this company have a very simple slogan, and this is right over here, and means the following. We have a lot of flame retardants on the market for a lot of applications, for bulk materials, for foils, for films, for fibers, and so for foams, and so on and so on. But what is the right one? We need. We don't need one. We cannot create one flame retardant for all applications. Most important are synergistic effects. That was their meaning, and that's why they said, okay, we synthesize we upscale two different flame retardants, so-called radical generators, and do some synergistic investigations. And this is shown over here. You see the three flame retardants upscaled and going for production. The structures will I show on the next slide. And you see here some synergistic possibilities. One for polyolefins, for foams, for ABS. First time we can have a non-halogenated flame retardant solution for ABS, TPU, thermosets, coatings, and as well wood. And again, here we see two of the commercialized structures, Songflame 205 and Songflame 201. And we see on the other hand flame retardant synergies, and these are the known phosphorus derivatives, this PCO 900 from Tor, the AHP introduced at the beginning, phosphocines works very well, APP works but not so very well, cis and that one are very, very active. Of course, also brominated stuff can be active. But it is also published over here from Kalle. Now, what is the amount necessary for get good flame retardants? This is for simple investigations in PP. You see here for brominated stuff, together with SP, with antimony oxide, you need 12 plus 5 for V2. PCO 900 alone, about 4, no classification, 8, no classification, 15% V2. PCO 900 plus 1 radical generator, 4 plus 1 V2, and 8 plus 2 close to V0. That means these radical generators are not only very active, they are much more active in synergistic formulations. and I think it's worthwhile to look a little bit deeper. Calle-Villain himself as well, and you see here the last publication from him. So now he's combining this NS groups in one molecule with phosphate groups and looked for in different manner and looked for their efficiency. Okay, coming to the conclusion. Okay, 1 hour. That fits. Interaction between flame retardants and their synthesis. I hope you will understand now a little bit more. Atom efficient synthesis routes. It's really important if you want to think on upscaling or on production. Flame retardants and anti-dripping properties. This is a very nice and interesting field because of possible banning of Teflon derivatives, the classical anti-dripping agents in polyamides and polyesters. Polymeric flame retardants are going more and more of interest because they have very nice properties regarding to the matrix polymer on the one side and less problems on registration. That's why synthetic routes, synthesis routes, are of interest. New starting materials are always interesting, in particular if this is cheap and very easy to get materials. And last but not least, I discussed about radical generators, especially in synergistic applications. Now, I'd like to thank you for your kind attention, of course. And I hope I can give you some idea. And of course, I'm here for questions, sure. Last but not least, I'd like to show you some impressions from Germany today or in these days. This is close, Advent side is close to Christmas. And you see here Christmas markets in a small town. Their special beverage is hot red wine with spices. And if you come close to that market, you will smell this. It is very, very intensive and very, very good. And you have, of course, special Christmas dishes. And this is only in a small town. This looks in a greater one, in a big town. You see a lot of people going from hut to hut, and they have special Christmas cakes and gingerbread and this mulled wine. Very interesting. Most of the groups like you at night don't go home. They go to the Christmas market. Okay, thank you very much for your kind attention.
Professor Manfred gave an excellent lecture about the phosphorus, different kind of the phosphorus, and the radical generator, the different kinds. Thanks very much. So now, any question do we want to start with?
Hello, Professor Döring. Very nice presentation. I have one question. When synthesize green industrial blender, that is the atom economy, selectivity, and the yield are important. Which is the most important?
All three together. Believe me. Okay. Look, industry is just looking for, last but not least, processes which have less synthetic steps. I can give you, in former times, I gave to my students lectures, we discussed only this. former times developed synthetic steps or synthetic procedures have often a couple of steps or a few steps, sometimes for drugs a lot of steps. And nowadays they do develop new synthesis for the same product which reduced the synthesis steps in a very strong manner. That means in former times perhaps 8, 10 steps, now only 2 or 3. It is now possible because they have new possibilities, for example, new catalysts, new starting materials to can do this. If you have a good yield, you have, of course, low side products. If you have a good selectivity, as well, low side products. And of course, atom economy means you introduce only small so-called helping materials like bases or acids to catch special products. That means as well low side products. All three things together should be optimized. Yeah? It's not only the side products, but of course, if you have a lot of side products, you are responsible as a company to handle this stuff. You cannot put it in the next river. It was in former times, but now it's gone. You are responsible for that stuff. And this is money. Okay.
In your lecture, that's the radiation generator that for the ABS and PP. That and suggest the additives is used just the NSR, yeah.
Yeah. This is NSR. Is
containing the sulfur.
These are these radical generators developed from polyethylene. Yeah.
This is important. I think that the phosphorus and the sulfur maybe the suggest is good.
I discussed with him a couple of times, and he said maybe we can develop others, but until now this combination of phosphorus compounds, special phosphorus compounds like this PCO 900 or phosphocines, and these NSR radical generators for such applications are the best one. And if you see this, which someone offered, if it is possible to create halogen-free solutions for ABS, which is not possible until today. Exactly. Or for other things, TPU or coatings and wood. Wood, especially, there are industrial applications. I show it because it is in Scandinavia, where polyethylene is coming from. Very, very popular now to build up wooden houses. They have a lot of wood, and this is very, very popular. But it must be flame retardant, and they use this stuff again for flame retardant, for forming flame retardant wood.
And this is just the PC, the 9.
Yes, these are
PC 90 and 90, and this combustion that NSR is combustion.
These things are commercially available. This one and this one. This is.
And also is PC is PC.
And this one 1 in 5. I think this number I have only the structures for that one. 201 and 205.
And this is the 900 is all commercial.
Which one? Yeah, this is commercially available by this British company Thor. They're producing this in Germany, close pretty close to BASF.
Ah.
Only 20 kilometers. Yeah. I can give you the address where you can order this. Yeah.
I have the question: how to prove the radical generator? Have some proof?
Very good question. The best way is I should switch to another talk, because, to my opinion, if you cannot prove something, it's only an assumption. You need evidence. We did it for disulfides, not for that stuff, but I think it's nearly the same. We were able to detect S2 radicals. He postulating these radicals over here. Of course, I think it should be possible to detect this. You need a special MS technique, for example, or you need a special laser technique. It's much better. It is possible, but it is not done until now.
So these radicals will trip the hydrogen radical, or
Will catch.
Yeah, will catch
the OH and O and H radicals, like PO or brome radicals.
Okay.
It's the same,
Okay.
but more efficiently.
Is it efficient compared with the PO?
No, it's more efficient.
More
efficient.
That's why you need so less amount of flame retardants.
And how much they say just?
I don't know. That is really it's strange. I don't know the Korean guy. We wanted to order this SN derivatives for comparing investigations, and ordered this in a company. Ordered this in Korea. No way. I called Kalle Wilén, of course. I said, Kalle, it's unbelievable. I think this company is selling this stuff. I said, yes. And I said, no, we cannot order. And he said, he will call these guys. He did it, but now I'm 3 weeks over here in China. I don't know what is going on, but this was really terrible to get this. And I don't know why. Because if I'm going for producing, I want to sell, I want to earn money. It was really strange. As well for Kalle Wilén.
Maybe one people will contact with you. Yeah, I understand the company. Yeah, maybe commanded is okay.
Yeah, Songwon is not a small company. They do a lot of production of stabilizer for polymers, UV stabilizer, but also other stabilizers, and are famous on the market. But I don't know what's going on. It was a plenty of information. Too much, perhaps, for one afternoon.
Okay. Maybe I think the students maybe
the door is open.
Okay.
Okay.
Thanks very much again.